So I am surprised, not Anas. Unfortunately, he couldn't make it, so I jump in and talk about rendering performance instead of what was he supposed to be talking about? Yeah, reactive something. It's, it's computers, so it's basically all the same. So I am a German living in Switzerland, in Zurich, where I do computering. I also have a very serious LinkedIn picture because Germans have no sense of humor. This keeps recruiters away, just saying. It's a really good thing to actually do that. The ones that do still contact me, I have a website that says this is an automated process. Thank you very much for your interest. Please transfer me $500 to proceed to stage 2. That does keep them away, unfortunately. I'm working in engineering. I'm the head of engineering at a tiny company called Archeologic. We are based in Zurich, but have a few 3D modelers around the world. What we do is we do 3D graphics in the browser. I'm also GDE. I am working with the Mozilla community, and I'm working with the W3C. So if you want to get into open source or help the community, give back something to the community, definitely talk to me. I'm happy to connect you to people, and please, please, please do stuff, because we're better together. Besides, my clicker just stopped working, and that is fine. So what we do is basically we allow you to get 3D content on the web more easily and more conveniently. This is the A-frame developer tools from Mozilla. We plugged into that, and then you can just basically get architecture models of whatever office or flat you've got. Or you can get furniture and stuff, and that's all free. And if you're super successful and make lots of API calls, eventually you're going to be like, hi, do we want to give us money so that we can eat and stuff? And that's going to be nice. But I'm going to talk about rendering. And when we talk about rendering, let's start from the very bottom. What we give the browser as the very, very first step is a bunch of text. That looks like that, more or less, right? We give them HTML. Or maybe JavaScript that ends up rendering some HTML that the browser can consume. The browser then goes through this piece of text and goes so what do we have here? A little like the US cops, well, what do we have here? We have a high headline, we have a link in the headline, we have a nav element, we have a few links in there, good. And then it creates a tree from that, because basically this is structured data, but it doesn't tell us much about the content in this form. So the first thing is the browser parses this into a tree. Now, I don't know about how you browse the web, but I don't see that in my browser when I go to a website, but this is still important. This is one of the 2 trees it creates. It's the DOM tree. You might have heard that before. Woo! And there's also the CSS object model. It's a tree that basically describes how CSS maps to this tree. And that's still not what we are seeing on screen. So the next step then is it takes the tree and goes okay, it's a little if you move into a new flat or something, it's more or less the same thing. You just go you have the empty flat and you go okay, so the couch goes here, and then the TV goes here, and the fridge is there. That's really good. Where do I put my couch table? So basically the browser now has to figure out how large is everything and where does it go. So the headline element spans the entire width of the window. The anchor goes into that. Then we have a navigation element. Maybe CSS moves that over and displays the anchors as block level elements within this. So basically it now figures out how large things are and where they go on the page. This is called layouting. The Firefox engine, Gecko, actually calls this reflow, but it's basically the same thing. And what happens here is good, but this is still not how my websites look when I look at them. So we somehow have to transform that into the actual pixels that we are seeing on screen when we actually visit the website. So the next step then is, why did I say one on whatever? Okay, never mind. Last minute presentation thingies, never a good idea. So the next thing is to actually color in the blocks that we've seen. So we have an H1 block with a bunch of text, cool. And then we have this nav block with a bunch of text, and then maybe there's other content as well. So we now have to color in the pixels by basically pixeling in one by one. While the browsers are faster than that, it doesn't take as long, but basically that's what we're going to do next. But how does that actually work? I mean, there's not going to be a little gnome showing up with watercolor and going, right? That's not going to happen. So what does painting actually mean? Well, consider the screen a gigantic array. Yes, sure, it is true dimensional, but basically you could say like, we start at 0, 0, and then go like, it's basically a very, very long list of things. And each of the things in there is actually, each pixel that we see on the screen is actually 3 numbers. It's a number for how much red there is, it's a number for how much green there is, and how much blue there is. This is RGB, right? It's 1 byte each. So that means that we have 3 bytes for each of the pixels we've got on the screen. And basically painting, all it does is putting the numbers into that list. Well, if you think about modern resolutions, you might think, wait a minute, so it's like 1 pixel is 3 numbers that we have to fill in, and we've got a lot of pixels, right? Full HD, that's quite a few pixels. For instance, Full HD is like 6.2 million bytes that we have to fill. And if I remember correctly, that's going to be not only 1 floppy disk, that's not only 2 floppy disks, it's not even 3 floppy disks. No, it's 3.2 floppy disks. So basically, whenever you're getting 1 picture, 1 frame of an animation or anything onto the screen, what you're basically doing is you throw floppy disks at the, just really quickly. So we basically have to transfer 6.2 megabytes of data for 1 frame. If we want to do that with 60 frames per second, that means that we do that 60 times in 1 second. That's not much time to do that. So basically, filling it all in within 60 frames per second means that we're having approximately 16 milliseconds. The browser needs to do some other stuff, like handling our clicks and things. So basically, we have around 10 milliseconds to fill in 1 frame. 1. That's not much. So what we're doing is we're trying to be smart. We're trying to say, how about this? I mean, not the entire website changes every frame. So could we not just like paint into different lists and then combine them? Wouldn't that be nice? Like I could use this background and fill it all over the place, and I have this tiny little cat here, and put it into different places on these 2 images. And basically all I'm doing is I have these 2 lists filled in already, and I just quickly copy them over in different places, and then that's my animation. That's pretty cool, and this is called compositing. And the cool thing about this is this kind of stuff is basically independent of everything that happens in the main thread, so we can do that in parallel. So we are not blocking the main thread. You can still click on things and stuff. You can still do it while we are compositing. It runs in the background. And it runs on graphics hardware, so it basically just doesn't take up too much CPU power. It's only a bit of overhead of getting like the lists and stuff. So basically what we're doing is we take a bunch of images, if you want to generalize that, run that through shaders, and then we get like an image where the things are like put together. That's very nice. Wait a minute, Martin. What are shaders? That sounds shady. One person got the pun. That's very good. Like, it's not that complicated. So to understand what shaders do, let's have a quick look at the hardware. So most devices today have 2 kinds of processors in there. Processors are basically rocks that we tricked into thinking. So we have the CPU that doesn't have as many cores, and we have the GPU that has many, many cores, many brains. It's tiny brains, but it's many of them. So a normal computer these days has like anything between 1 and 16 cores probably. A phone probably around like 8 cores if you have a high-end phone right now. It's like 4 cores if you have a non-so-high-end, and so on and so forth. And these usually are the CPUs. But GPUs usually have a few thousand cores. Now, obviously, you always want more cores, right? Because more is better, right? That's not quite true. Because actually dealing with a lot of, it's like try to divide the work between you and 1 person and try to divide the work between you and 1,000 people. If your flat is tiny and you're trying to tidy it up, that's not going to work really well, unless these 1,000 people are really, really good, so like in interpersonal communication, but that's not going to work out. And we have a similar problem here. So the CPUs are optimized to solve certain problems that look like this. So I have a list, I have a loop, and I want to read something from the memory somewhere, add something onto this address. Like basically I have a starting address, and I take something from a later address, and I check if that value is 5, and then I write to another memory space somewhere else, and basically this can overlap, and I can't just give this out. How do I divide this between 1,000 people? That's not really easy to do, right? Because what happens if someone then basically has to wait until this is written to read it and then deal with it later? That's not, it's annoying. So that the GPU cores are not really dealing with this, and the CPU goes like, yeah, this is my cup of tea. I'm doing this kind of stuff. Give it to me, sure. But there are other problems as well. Other problems where this is not necessarily a good thing. So the CPU deals with like parallelism and like locking memory regions and making sure that things are executed in order and stuff, but it's not really good to do things that need parallel execution. And that's where these little fellas shine, right? So let's say, for instance, we have matrix multiplication. So to multiply two lists, or two matrices here in this case, we take this and this, put that here, we take this and so on and so forth, basically, and it's the same operation, it's just on different fields, and they don't depend on each other. It's not like the value of this field is A if this is 5. No, that's not true. It's always just like we take different positions and put them together. So it's like relatively easy to divide. I could say, okay, you here, you do this part, and I do this part, and then we divide that. It's easy to divide, so the GPU architecture really goes like, yes! I can do that, and the CPU goes, woo, I can do that, it just takes a little longer because I do one thing at a time, which is not fully true. I'm grossly oversimplifying, but you know, deal with it. It's a 30-minute talk, not a 6-month lecture, so here we go. But yeah, okay, cool, but what does that mean in terms of, you know, pixels and rendering and stuff? Well, this is like an array, right? Array of things. And the pixels are basically also an array. We have established that. So here we have a very simple case where we have one core for each pixel. That's not always true. It's normally not true, actually, but for the demonstration purposes, I'm doing this. And what can I do now? Well, if I want these to fill in the pixels here, I can say, well, all these have coordinates, and I can say like x and y is like 0, 0, so x is 0, y is 0, x is 1, y is 0, and so on and so forth. Y is 1, x is 0, and so on and so forth down here, right? So I have my 4x4 display. Probably like an old Nokia phone has more pixels than that, but okay, that's, you know, they are large, so it's fine. Really high resolution here. So what I do then is I give them a task, and I say, look, I give you a function with the x and y position that you're responsible for, and you produce me the color value, which is 3 numbers, right? We have established that, red, green, and blue, by taking your x position, multiply it with 85 for red, do the same thing for the y position for green, and just don't use blue. And then in one go, one step, boom, colors. With a CPU, it would have been like, okay, 0, 0, 0, 0, 0, 0, black. All right, next one. Okay, so 85, 0, okay. It takes ages for a CPU to do that performantly and fast. I mean, it does work, but the GPU is perfectly made for this. It's specifically designed for this kind of tasks. And guess what? You have just learned what shaders are. That's a shader. It's a function that takes a bunch of inputs, does not depend on other results from other cores, and produces a value. In this case, it takes the x position, the y position, and produces red, green, and blue values for the pixels on screen. We could also add in other things. We could give like pixels from different images that we rendered before. So we could have like our background color, we could have the color from the Nyan cat, and then figure out how we combine them using math. Yeah. Math, holy shit. If my teachers would have told me that I can do like pretty things with math, I would have probably listened better. So if you have a kid in school, just go like, you know what, you want to do like games and stuff? Yeah, math is the answer. So what can shaders then do? So all these operations turn out to be actually pretty powerful. It starts with moving things around. Because I can basically take an image, a pixel from an image, and then say like, and write that there, right? I don't have to write it into the same position that I'm running for. I can write it somewhere else. If there's another function run later on that addresses the same pixel as the output, then sure, I'm overwriting it, but I can do that. So I can move things around in shaders in one snap, in one go. I don't have to do that via the CPU. I can also rotate things. That's a matrix multiplication. Let's not do that. But you can totally do that in the shader. You can rotate things around in all 3 dimensions if you use large enough matrices. You can also scale. I just like render the same pixel multiple times, or less than once if I'm scaling down. I can also figure out opacity, because basically what I do is I take a value, I multiply that with another value, the opacity value, how much of it I want in there, and then I add the other things multiplied with their opacity, and then I get the right value at the end. So these are the things that I can safely do. I can actually do more things, nicer things. They're called filters and blend modes, but browsers are not necessarily implementing them in shaders. That has a lot of technical, complicated reasons. You can totally ask me about them, and I'm going to lie. No, I mean, there is, just bring like a day, and I'm happily explaining how this works in detail. But so there can be done, like more things can be done in shaders, but not all browsers do it as a composite-only thing. Some browsers actually do paint again. So it's a bit tricky. So let's have a look at an actual application kind of thing. So this is a problem that you might have solved yourself or use like a component for solving. It's a menu that fades in and out. Very nice, very cool. That's easy to do, right? Well, let's have a look at what happens under the hood. So developer tools have this lovely feature where they flash the bits and pieces that have repainted. So that's not just the shader has run, it is actually having refilled the array, which we know takes a little longer because we have to do, you know, it's not very fun. So what we don't want is we don't want this to paint. The next slide, if you have epilepsy issues, do not look at the next slide. I'll give you you know, an all clear after we are through this. But the next slide is going to show with a different color whenever we are painting, which is something that we want to do as few as possible. Right? Wow, okay. How many repaints are these? I don't know, but it's clearly repaint disco. So you don't want to have repaint disco, you want to have as few paints as possible. And if you look at the timeline, you see like this is when the interaction starts. This is when the entire like thing starts, this is when it ends, and this is when I do it again. So there's a lot of green here. Green means painting. And you see the frames per second up here, like you want to be on this line, but we have a few serious drops here, and if this would not be a MacBook Pro, but a slightly older phone, this would not look good. This would go like you know, people actually physically pushing the menu in and pulling the menu out. Very tedious. So what we want is we want nothing here, but we have a lot going on. So now comes the interactive part. Shit, he said interactive, so that means like, is he asking questions? Yes! I'm going to ask you questions. But don't worry, it's going to be fine. I might even have Swiss chocolate that I give out to the right answers. Yeah. Let's see. I might. I'm not sure about this. Okay, let's have a look at the code. So here we have a bit of CSS. Ugh. Don't you do that in JavaScript these days? No, I love, like, CSS is the shit, really. It's like, mwah. Anyway, moving on. So we have a transform on the element that we translate x it to 0, whatever, so nothing really happens. But after 2 seconds, we are changing the style to actually move 200 pixels to the right. Will it paint? Will it? Yes? No? Maybe? No. Okay. No? Who thinks no? Okay, a few people. Who thinks yes? Who's just checking their phones and going like, what the fuck is the guy doing? All right, let's have a look. So remember, it flashes when it paints, right? So we're going to see like a flash of color when it paints. Oh no, I mean, it's so happy, but look at that green rectangle of sadness. That's not good. But Martin, we need to talk. It's not me, it's you, Martin. You said shaders can do moving things around. So why the fuck does this not do it? Why the flip does this not do it? Not swearing on stage. That was a technical term. So, well, you know, compositing requires layers. We have to have these different images. But if we have different images, they take up memory. And if we have 1 million different DOM elements, then that's going to be a lot of memory. So we're not going to have a layer for each of our elements. We want to be smart about it. And the browser conveniently does that automatically. The browser goes like, yeah, it's a website. It's just going to put everything on one layer and we'll be good. Except when the browser sees a few things that it doesn't like. For instance, if there's like a video element or a canvas element that is supposed to change a lot, then it goes like, yeah, maybe I just give it a little bit of memory to it so that we can like do this in compositing. The same goes for 3D transforms, because these matrix multiplications are usually super annoying. So it goes like, okay, fine, you do a 3D transform, so yes, let's do this, it's fine. That's why the translate Z hack works. Translates that, the browser goes, ooh, there's something going on here, and it's Z, so it's like 3D stuff, so yeah, I'm just gonna put that onto a layer. Don't do that too much, because then you cost more memory. That's not good. So, and then there's transform-only keyframe animations. It doesn't matter which kind of transform. If it's a keyframe animation, the browser goes, oh, I have to do this a lot of times, so yes, sure, let's put that onto a layer as well. So let's have another round of this. Slightly different code. Slight difference. All right? Din 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 din. Will it paint? No. Why not? Holy shit, yes, it's 3D. So does it paint? No. Yes! No green rectangle of sadness. That's making me happy. High five, man. Good job. Let's go have a beer. So yeah, this is really good. This does what we wanted. That's easy, right? That's totally obvious what's going to happen. But how about another round? Last round. Okay. Slightly more code. Slightly different code as well. So yes, does it paint? Yes? No? Maybe? I like bread. Okay, yes, we can see it again. Yeah, do it in the Jeopardy style. What code does not repaint? And the answer is yes. It does not no, it does not repaint, because it is a transform-only keyframe animation. So the browser goes like, yeah, this is going to happen. It's a 2D transform. That's boring. I'm not going to make a layer for it. But it's going to happen multiple times in a row, because there's going to be an animation with it. So yes, let's put it on a layer. Let's composite it. It does not mean that if you're using keyframe animations for anything else, that automatically creates a layer. For instance, if you're saying in a keyframe animation change color, we have to repaint the pixels, so there's no way around it. If we make it like larger and it pushes other things around then, because it's not absolutely positioned, that's not going to work either, and so on and so forth. So be really careful what you're doing. Some browsers even repaint on opacity changes. I'm not going to name any names. Microsoft. But also actually Safari, I think, repaints as well. It's only Firefox and Chrome that are not doing that. But it changes quick. They're like Hicks und Draconis, here be dragons. I am not sure about this. So, yeah. So what we've learned is there's a bunch of things that we have to look at when it comes to rendering. And rendering, what we want to do is there's a bunch of steps that happen. It starts with parsing. We can't really do much about that. It goes on with layout. We can try to avoid shifting things around using layout calls as much as possible. There's also the thing called DOM thrashing, when you like change the style and move things around on the page and then query the data right away and then do it again. That's also not good. And then there's painting. That's annoying, but we have to do it sometimes. We have to repaint. But if we can, we want to skip all the work. As Paul, which one? One of the Chrome Pauls once said. Paul Lewis once said, performance is the art of avoiding work. Don't say that in a like performance interview with your boss. That's not going to fly. But generally, performance is the art of avoiding work. So we want to get as much composite only as we can possibly have. And there's also the new property called will change. That's really handy as well. Not all browsers support it yet. It is less easy than it looks at the first time. I should probably blog about that. But basically, will change gives you a possibility to also force layer creation where you need it. Do not create layers because it makes it more performant. No, only use layers when you see a performance problem in your animations, or try to make it a composite-only animation as much as possible. And I hope that clears some of the things up, and I hope that you're having fun building the next cool stuff. Thank you very much.